Hello, my dear students. Now, this is the final part, the third part with our amplitude modulation lecture. In the previous two parts, we have investigated together different ways in order to implement amplitude modulation. We have understood the concept of a modulation index and modulation depth, and also we have investigated the different schematics used in order to do what's called a demodulation process, which is the process of transferring back the passband signal into a baseband signal. This lecture, or this part of the lecture, will be dedicated to explore more about the different techniques of amplitude modulation in terms of bandwidth and power. As I mentioned in my previous lectures, and in this lecture as well, that bandwidth and power are always equal to money in the communication industry. So, what are the bandwidths for different AM implementation? How we can calculate the power? And maybe we will terminate the lecture with some demonstrative show using one of our in university implemented Java codes in order to demonstrate some AM signals in time and frequency. So now permit me to start sharing my screen and to continue our amplitude modulation lecture. Okay, now I believe you can see my presentation slides. Let me start using the pointer for this presentation with the amplitude modulation as lecture number 3 in our Introduction to Communication Systems course. Okay, perfect. Let's start. Here, this is the modulation technique. I believe we already have investigated all these slides and we have investigated the concepts of the amplitude modulation, frequency modulation, and phase modulation. Also, we have understand the concept of the DC offset, and maybe we will return back to it in the beginning of this lecture. And also, we know the profile or the envelope of the carrier, the modulation depth, the frequency domain analysis of a double-sided band AM signal, and also some demodulators. We investigate in part 2. If you remember, my dear student, sorry, we investigate in part 2 the concept of the square law demodulator and also the concept of the coherent demodulator, where we investigate the need of having a copy of the carrier here in order to multiply the signal with the carrier. Maybe in our extra session, we will going to discuss more in depth the effect of changing the phase and the frequency of such a carrier with respect to the original carrier included in SOT. So this is maybe discussed later on. But let's now go back to what's called bandwidth. Okay, so first of all, we have to define what is the bandwidth. Bandwidth is basically the portion of frequency dedicated by the signal. So whenever we have a baseband signal like this is an M of F, which is a frequency domain analysis of the Fourier transform of a message M of T. This message, for example, a random message, has a frequency portion extending from F1 to P. So this is the bandwidth of this signal. Now, what if we modulate this signal using double-sided band AM modulation? You should expect the output frequency, the output frequency spectrum. So if we are using a double-sided band AM modulator, we should have an output signal in this way. We have a carrier located at FC, and then we have the two sides of the signal, what's called the upper sideband and what's called the lower sideband. As I mentioned in part number 1 and part number 2, this is basically a redundant signal. So messages included here is typically included there. So we are sending two copies of your message in addition to the carrier. This is the output of your double-sided band AM modulation. Now the question is, in order to transmit this message over an AM signal using double-sided band AM modulation, how should be your bandwidth? What is the bandwidth needed? So basically, the bandwidth needed is this region, starting from the minimum frequency you have, which is FC minus P, till the maximum frequency you have, which is FC plus P. This is the total bandwidth that you need to dedicate, you need to buy in order to send your message. So that means that you need a bandwidth too. Here, the main, or not the main, one of the disadvantages, maybe the main disadvantage of the double-sided band AM starts to appear. Why is it a disadvantage? Because basically the original signal, the message has a bandwidth P. However, in order to transmit this message, you need double the bandwidth. You need 2B in order to transmit this signal. That's why this is somehow a wide bandwidth, a large bandwidth. As I mentioned, bandwidth is money. Whenever you need more bandwidth, you have to pay more and more money to the government or to who control the bandwidth you are sending. So now let's see how we are implementing this. Herein, I start to show you another block diagram in order to do the double-sided band AM modulation. Actually, I am attempting now to confuse you because the old block diagram was in this shape, if you remember. Oh yeah, this is the old block. Here you have K, which is what we call the modulation index. We have one as a DC offset, and then you multiply by the carry and so on. Now we have another block diagram for the same signal. Here is the one. So, my dear students, let's investigate this block diagram together to check if we will get the same output or not. So let's do it. Let's now go to our simple whiteboard and let's turn for a while the, okay, I have to adjust the camera a little bit. Okay, I think this is okay. So that's one. Okay. So what is our block diagram? Okay. Let me copy and paste it from the presentation. It has, or it looks like that. We have some voltage called VDC applied on an adder. The other input is the message. Then we have an RF mixer with cosine 2 pi FCT, and then this is this. So this is basically the input block diagram. So, for example, this may be your final exam question, your in-class test question. So please don't get shocked whenever you see a block diagram which is not typically like the one you see in the lecture. It's very simple. Just follow the mathematical analysis step by step and see what will be your output SFT. So here we have two added signals, VDC, which is a DC offset, and M of T. So what is here is simply VDC plus M of T. Now, this VDC plus M of T will be multiplied by cosine 2 pi FCT. So you can now write an equation for S of T. So S of T will be equals to VDC plus M of T cosine 2 pi FCT. This is simply that S of T signal. Now, in our previous lecture, part of the lecture, we have somehow a different look. We have an amplitude which called AC. Let me write it with a different color in the same slide. So I will use, for example, the black one. So let me write. So our oldest SFT looks as S equals, if you remember, AC 1 plus K M of T cosine 2 pi FCT. You remember this? This was our AC signal, modulated AM signal. Okay, now we have somehow a different look, as you can see here. So, can we make some sort of analogy between this blue S of T and this black S of T? Can we do this? Let's say, okay, so now, if we have VDC here as a common factor, so we will get S of T equals S of T equal VDC, and then we have 1 plus M of T over VDC cosine 2 pi FCT. Now, more and more closer, this VDC is corresponding to this AC, and this 1 over VDC is corresponding to K. So, for example, if this M of T is Vm cosine M of T, for example, cosine 2 pi f M of T, then the ratio Vm over VDC will be K. Again, let me do it. If this M of T is, for example, Vm cosine 2 pi fmt, then simply from this analogy you can say that K is equal to Vm over VDC. We will use it later, but this is very important. So this is K, what's called the K, which is a modulation index, or sometimes we call it, by the way, M, the modulation index. Both are okay. I believe that high K may be used M. I'm not sure, but I believe that high K use M. Maybe in my previous part of the lecture I used K, but by the way, both meaning by the end of the day, let's call it the modulation index. So both will be or will have the same meaning. Okay, so now from this simple mathematical analysis that you can, I'm sure that you can easily do, you can easily prove that this plot diagram will end up with typically the same like what we got in the first part of the lecture. So we can have different block diagrams demonstrating same idea. Okay, that's perfect. Okay, let's now return back to our slides. Okay, let's be sure the screen again. Let's read our point. Now, we understood from this slide that we have some sort of, let me say, a disadvantage in the double-sided AM modulation, which is that we need a bandwidth of 2p. The original signal bandwidth, let me remember that the original signal bandwidth was just b. However, you need double the bandwidth in order to transmit signal. Now, what should we do? Okay, let's go to the first idea, the first extension from the double-sided band. So the double-sided AM is the standard way. And now we are going to go to somehow an updated ways from the double-sided band. The first one is what's called the double-sided band suppressed carrier. So we suppress, we reject, we kick out the carrier. So what we are doing simply is that we will just multiply the message with the carrier. We will just multiply the message with the carrier. And then the output is simply the message multiplied by the carrier in a very simple way. So now the output is M of T cosine 2 pi FCT. The modulated signal. There is nothing, there is no DC offset, there is no shifting, there is no separated carrier. So you can easily expect now that your frequency spectrum will look like that. You still have both sides of the AM signal or the message, the upper side band and the lower side band. Of course, the upper is called the upper because it's at higher frequency, and the lower is a relatively lower frequency. That's why we call it the upper and the lower. But as we mentioned, both are identical, so no difference between both. So now this is the upper side band and this is the lower side band, and no carrier exists. But here you should stop me and tell me, yeah, this is too stupid. Why? You are doing this update in order to reduce the bandwidth. But unfortunately, you are using the same bandwidth. You're still using a bandwidth 2B. Nothing has been changed. Okay, you're right. However, one of the advantages of this system is that you reduce the power needed, which we will talk about later on in this lecture. So please keep this in your mind. Okay, believe me, somehow that this is a good way. However, we still have the 2B bandwidth. Okay, I agree with you, but we will return back and see the advantage of this system over the double sideband AM. Then, what's next? Okay, so you can stop me here and tell me, okay, you have a bandwidth of 2B simply because you are sending 2 copies of the message. That's why you need to double the bandwidth. If you send only 1 copy of the message, you will not need this huge bandwidth. So what we are going to do is very simple. What if we insert a low pass filter? So we have a typical double sideband suppressed carrier. Here, this is a typical double sideband suppressed carrier. The same like the one you show here. Typically it's the same. An RF mixer with a message and a carrier. Typical. But what is new now is that you have a low pass filter, or not, I'm sorry, not a low pass filter, a band pass filter, which should only pass 1 copy of the signal. This ideal filter response. If you remember the end of lecture number 1, when we introduced the 4 types of filters: the low pass filter, the high pass filter, the band pass filter, and the band stop filter. This is an example of a band pass filter. You have a band pass filter which can only pass this window and kick out this lower side band. So you will get only this new frequency spectrum where only a bandwidth of P is needed in order to transmit your signal. You only need this B value of bandwidth. So now you can reduce the bandwidth of your signal by using what's called the single sideband AM modulation. So based on that, we have studied that AM modulation can be either a double sideband suppressed carrier, single sideband, and as I mentioned in part number 1 of this lecture, we have another fourth way or a fourth technique called a vestigial sideband, which is out of scope of this course. Maybe you can refer it when you go to section 2.2 in Simon Heiken, chapter 2. So you can go and check what is the vestigial sideband if you are interested to know more about the vestigial sideband. So this is the single sideband. Now, let's turn the page and let's go to what's called the power consideration. This is actually, my dear students, a very, very, very important example in order to understand the comparison between the double sideband and the double sideband suppressed carrier AM modulation. So here we have to have some sort of introduction before going to investigate more in the double sideband and the double sideband suppressed carrier power considerations or power management. Okay, so let's first start from scratch. What is power? Okay, the electrical power is a relation considering the voltage current. So power equals V times I. Or power equals V squared over R. Or power equals equals I square. These three relations, knowing that of course V equal IR, which is on flow. So using these three relations, you can calculate the electrical power of a signal. But usually when we are going to demonstrate our signals, we are only using voltage. I believe in any communication book, if you go to Simon Hyken or any other reference, you will never see something about current resistance. Okay, so in order to make life easy, we can say that power is directly proportional to the voltage square, where the proportionality constant here is simply this 1 over R. So if we assume a unit resistance, I mean R equal 1, we can say simply that power is equal to V squared. So usually in communications, my dear students, we just use power equal to V squared. That's all. And we are assuming that R equal 1. Okay. Now, the next question is, do we deal with an exact deterministic signal? I believe that all of you know the sinusoidal signal. For example, when we are dealing with a carrier, for example, let's start with the carrier. So we can say that our carrier is equals to VDC cosine 2 pi FCT. This is our carrier, for example. Now, for this carrier, you have two choices. What is this VDC? What do you mean by what is this VDC? Is it an exact VDC? Of course, nothing exact. There's some sort of equation. It's random. So you will choose that this is somehow what's called random. Sorry, not random. A root mean square value. The RMS value. This is the RMS, of course, the most famous example when you are dealing with the AC coming to your flat, the electricity. This 220 voltage. This is a root mean square value. It can be 210, it can be 230, it can be 240, it can be 190. The average, the root mean square value is 220. So whenever you are going to calculate the maximum value using this root mean square, you know, I believe that this V max is equals to V root mean square over root 2. I believe you already see this piece of equation before somewhere in the circuit, or maybe in other probability courses or something like that, maybe in mathematics. So normally speaking, my dear students, whenever we are dealing with any communication signal in an AC format, we will say that the power equals to the voltage of this signal square over 2, which is simply V over root 2 over square. So this is a rule. You will use it everywhere. Just pick up the voltage and then square it, and then you will get this signal. Okay, perfect. So this is the first piece of information. What is the second piece of information? If you have an input signal, message, M of t equals to Vm cosine 2 pi Fmt. And I told you, please, my dear students, please plot the Fourier transform or plot this frequency spectrum for this sinusoidal signal. You told me this is a very easy question. I can make it in one step. So this is very easy. So this is the M of f, and this is the f-axis. Now you have a frequency. It's called fc. Sorry, fi. So we have here a delta Dirac here at the frequency fm, and another delta Dirac here at the frequency. That's perfect. But you are one information, which is what is the amplitude of these two deltas? If you remember from your signals course, the amplitude of these two deltas are simply half of the maximum amplitude. So Vm over 2 and Vm over 2. So as if you are dividing that total voltage into the two signals. So, okay, so now these are the two pieces of information needed in order to do our exercise. Okay, let's do our exercise. I will return back to these slides maybe 1-2 minutes from now. Okay, so in the final exam, I told you, my dear students, you are doing now double-sided AM modulation. Your carrier is VDC cosine 2 pi FCT. And your messages M of t equals Vm cosine 2 pi Fmt. First of all, please plot the frequency spectrum for such a double-sided band AM modulator. So, very simple. You will say that, okay, this is double-sided band AM modulated. So, we have at FC, we have a carrier with a frequency VDC. Sorry, I'm sorry, with an amplitude VDC. And then we have a copy of the message here. So we have here two signals. This frequency is FC plus FM, and this frequency is FC minus FM. The amplitude here is Vm over 2, and the amplitude there is Vm over 2. That's right. So this is the output AM signal. I believe all of you know the signal. So now we are going to calculate, of course, you have a typical system here. So this is just an axis of symmetry. So you have a typical signal here, but I'm not interested, of course, with this. This is just a replica, a redundant image. So I'm just going to calculate the real power, which is in the real frequency of the positive frequency axis region. So if I told you, please calculate the overall power from the signal, you will say it's very easy. Now, in order to calculate this power, so as you can see, here we have three sinusoidal signals. So the total power is equals to the power of the carrier, this red peak, plus the power of the upper side band plus the power of the lower side band. Very simple like that. Perfect. So P total is equals to, now you can do it. For the first portion, which is the VDC, we apply the rule that this is VDC is over root 2. So we have VDC over root 2 whole square plus here the magnitude is Vm over 2 over root 2 to make it a maximum value square. Similarly, of course, for the third portion of the curve, so it's Vm over 2 over root 2 square. As you can see, very easy. So So if you return now back and you would like to make the equation more and more simple, you will say this PT is equals to VDC squared over 2 plus VM squared over 4. No, it's not 4, I'm sorry, over 8, because 2 squared will give 4, and root 2 squared will give 2. 2 times 4 will be 8, and plus VM squared over 8. Or simply, you can say that PT is equals to VDC squared over 2 plus VM squared over 4, which is simply the calculation or the summation of these two terms. Okay, that's perfect. Then what you are seeking for, this is just a mathematical steps. So now, what you can do is as follows. You will say, okay, so you will say the part total is equals to, I will just repeat the equation. So VDC squared over 2 plus VM squared over 4. Okay, what if I take VDC squared as a common factor? Then you will have, maybe I can take also VDC squared over 2 actually as a common factor. So then you will have 1 plus VM squared over 4 over VDC squared over 2. That's right. Which is simply as follows. So PT is equals to VDC squared over 2 plus 1 plus. This will turn to be VM squared over 2 VDC squared. Okay. Do you remember VM over VDC? Do you remember this? Okay, let me return back. My first slide today. Here. In this slide, he told you, if you consider the message is M of T cosine 2 pi FCT, and this is your carrier, then VM over VDC is simply M or K, or the modulation index. Do you remember this? So now I can remove VM over VDC and put M or K, the modulation index. So the equation will be as follows. So what I do with that is that I will remove this and I will put M. So PT is equals to VDC squared over 2. 1 plus M squared over 2. Okay. Till now you can consider this is some sort of a rubbish mathematics. You're just doing some steps, step by step, and now you calculate the total power of the signal. Okay, it's okay, very nice. But how I'm going to use this, or what is the concept beyond this power? Okay, that's sort of thing. This is the total power of the signal, including the upper side band, the lower side band, the carrier, everything. This is the total power. But what is the information power? What do you mean by information? Okay, let me return to the frequency spectrum. So do you remember this? my dear students? Yeah, in this graph, I'm just trying to keep slides in order so that I can make a good scan for you and submit it to you over the e-learning. Okay, do you remember this? Where is the message? The message simply is this blue curves, blue sparks, these two blue dilated direct functions. These are the messages. Are both the messages? No, there are two copies of the message. So each one independently is a message. Each one or any one of them is enough. This is the information you are sending. So what is the power of this information? Very simple. I can calculate it here. So if it's a sinusoidal with a magnitude Vm over 2, so simply, what you can say that the power of the message is P message equals to Vm over 2 all over root 2. Oh, sorry, I'm not rectangular. So again, that is a square, which is Vm squared over 8. This is the power. This is the information. Now, my dear student, we can make a very important ratio between the needed power and the total power. Please don't forget, power and budget are money. Power and budget are money. So what you are sending is this total power. What do you really need is this power. This is simply the difference. So this ratio will indicate how percentage of the total power is really needed by the receiver. How percentage is the message. So let's do this exercise. So Pm over Pt equals Vm squared over 8 over Vdc squared over 2 1 plus m squared over 2. Again, what I did here, my dear students, is simply that I divide this term over this term. So now, as you can see, here you have 2 and here you have 8. So this will turn to be 4. Here we have 1 plus m squared over 2. And here again, we have Vm squared over Vd squared, which is again m squared. That's right. So by very simple multiplication for these 4 inside the bracket, we get Pm over Pt equals m squared over 4 plus 2 squared. Okay. Here we have to stop and observe. Remember our technique. Solving an example, reaching an answer, start to observe. Okay. What do you mean by this? Okay. Do you remember the fair value of m? Do you remember? The fair value of m was 1. If m is smaller than 1, then you have what's called an under-modulation. If m is greater than 1, you have what's called an over-modulation, if you remember. So, if m is equals to 1, what will happen? If m is equals to 1, then you will have, so for m equals 1, you will have this ratio Pm over Pt will tends to 1/6. Can you imagine? You only need 1/6 of what you are transmitting. 5/6 of what you are transmitting is with no need. It's just a carrier and another and the other image of the the carrier and the other image of the message. If you determine the percentage of the power of the carrier, you will find that in this example, PC over P total equals to 4/6 or 2/3. 66% of the power you are transmitting is in the carrier, not in the message. So now you can understand what is the advantage of the double-side band suppressed carrier, where there is no carrier transmitted. Whenever there is no carrier, then you are saving 66% of the power. Again, power is money, so you are saving money. Now you can understand the advantage. So when you turn from double-side band to double-side suppressed carrier, okay, you are using the same bandwidth, which is 2P. However, you reduce 66% of the power. When you turn to single-side band, again, you are reducing power and reducing bandwidth. But, my dear students, don't forget, no free lunch. In life, no free lunch. Whenever you are reducing your bandwidth, whenever you are reducing the power, you will need more and more complicated and sophisticated demodulator. And the probability of error starts to increase in the detection. So if you will pay a lot with the bandwidth and the power, then you will get a better received signal in the demodulator. Whenever you will pay less for a power and bandwidth, you will get less quality signal. This is life. So this is a very critical and important example to understand the amount of the power consumed by the carrier with respect to the total power and the amount of power consumed by the message with respect to the total power. This is very important. Okay, so I hope that you got this message well, because this is actually a very important point while we are dealing with double-side band AM modulation or different AM modulation techniques. So let me now return back to my presentation slides again. And let's do the point. Let's operate our pointer. Okay, so this is simply what we have did. This is okay. So this is the power. We have the power of the carrier, the upper side band, the lower side band. We determine them with using this equation, and then we make this total power. After that, we calculate the ratio, where we get this ratio, as you can see, m² over 4 plus 2m², which is typically what we get. Thanks God. And then we get the ratios, which is very important. By the way, maybe one of my interesting questions to you, you can consider it as a bonus, you can consider it for your final and E-class test exam, is that please try to plot this ratio versus m. So put m in the x-axis, put this ratio in the y-axis, and start to plot. Of course, m will never be equals to 0, because m is Vm over VDC. So in order to make m equal 0, that means that either the message equal to 0, which is impossible, so you don't have a message, or the VDC tends to infinity, which is again impossible. So m will not be equals to 0, so you can start with a smaller value of m, for example 0.1, 0.2, and then you can reach m equal 1, and then you can go for higher m, which is what's called overmodulation, and so on. This is actually very important, maybe to understand more these modulation concepts on the modulation. Okay, so let's now turn to our final slide in this presentation and in this lecture. This is one of the advanced AM modulators, where you are going to transmit 2 messages simultaneously. You are going to transmit 2 messages at the same time. How we are going to do so? It's very simple. This is your first AM modulator. As you can see, I'm using a cosine AC cosine 2 pi f, which is a carrier, and this is the message, and this is just a mixer. So you get here double-sided band surface carrier, AM modulated signal, as you can see. Then you pass your carrier over a 90-degree shift, 90-degree shift phase shifter. So you get, or negative 90, I'm sorry. So you get AC sine 2 pi f. So you have AC cosine and AC sine. And as this is a 90-degree shift, we call it a quadrature carrier modulator. Later on in our digital modulation techniques lecture, we will talk in more detailed manner about that quadrature modulation. It's very important digital. However, this is just an introduction to this concept. So now you are using a cosine and a sine wave. They are orthogonal, they are perpendicular. So we are using this feature in order to modulate M1 and M2. And then you make just a direct submission. In the receiver, you split your signal, and then you do a demodulator in this manner. So you multiply here by cosine and multiply here by sine. So here you will extract the first message, and here you will extract the second message. Of course, you need a low-pass filter, as usual. So I encourage you to do this mathematically step by step. To see here what is the output S of t, and then to go to this S of t and start to split it here and go deeply inside till you reach your M1 and M2. This is maybe, from my point of view, this is a very good exercise to make sure that you understand well the AM modulation. Now, my dear students, this is the end of this lecture. As usual, your feedback through heating feedback sessions is usually appreciated. Also for negative, of course. Negative is better than positive. Now, to encourage us to do better in our next lecture. Thank you very much, my dear students. This is the end of our amplitude modulation lecture. In the next lecture, we are going to go through what's called the phase modulation, including the phase modulation and the frequency modulation in one lecture. By the way, the content included in this lecture is the content needed from you in order to perform your in-class test, which will be implemented in week 8 inshallah. Thank you very much, my dear students, and see you in the next lecture. Bye.